Hello everyone, welcome to my talk. I'm Shujoy. I'm a postdoctoral researcher in the Algorithms Research Group of Université Libre de Brussels, Belgium. I will be talking about planar bichromatic bottleneck spanning trees. This is a joint work with Karim Abu Afas, Paz Karni, and Joseph S.P. Mitchell. Let P be a set of points in the Euclidean plane, and the objective is to find a connected tree that spans over all points, which brings us to the Euclidean minimum weight spanning tree of P, that is a minimum spanning tree where the weight of the edge between each pair of points is the Euclidean distance between these 2 points. Another variant of the Euclidean spanning tree is a bottleneck spanning tree, which is a spanning tree whose largest edge length is minimum. The question is why bottleneck is an important criteria. Bottleneck is a phenomena in which the performance of an entire system is severely limited by a single component. More formally, a bottleneck lies on the critical path and provides the lowest throughput. In combinatorial optimization, the bottleneck problems are those in which the objective is to find a feasible solution such that the largest cost coefficient elements have the minimum cost. Then in geometric networks, the bottleneck is defined as the length of the longest edge in the network. Bichromatic point space is a set of red and blue points in D dimension. Bichromatic spanning tree of these points is a spanning tree such that every edge of the tree connects a red point with a blue point. Planarity or non-crossing is another important aspect of a spanning tree. A spanning tree is planar if its edges do not intersect each other. An important point is to note that Euclidean minimum spanning tree or bottleneck spanning tree on monochromatic, meaning the uncolored points, is always planar. Because if there are 2 edges that intersect each other, it is possible to convert these to an alternative solution while reducing the cost of the solution, and these 2 edges do not intersect each other. But this is not the case for the bichromatic points. So what do we want? We want our tree to be bichromatic. There should not be any edges between 2 red points or 2 blue points, but always edges between a red point and a blue point. We want the cost of the longest edge of our tree to be minimum. And then we want our tree to be planar or non-crossing. Formally, given a set P of red and blue points in the plane, our objective is to compute a bottleneck planar bichromatic spanning tree of P, in which we seek a planar bichromatic spanning tree that minimizes the length of the longest edge. There are related works. Borglet et al. Studied the minimum weight variant of this problem. For points on a general position, they showed that this problem is NP-hard. Moreover, they gave a square root n approximation algorithm. Then for points in convex position, they designed a cubic time exact algorithm. Later, Binias et al. In Algorithmica 19 studied the problem of computing the maximum weight planar bichromatic spanning tree and gave a 1/4 approximation algorithm. Bichromatic bottleneck full Steiner trees problem have been studied, where the new points can be added to improve the cost of the solution. And Abu Afas et al. Studied this problem and showed that this problem is polynomial time solvable for arbitrary many Steiner points. However, it becomes NP-hard when there is a budget of using at most k Steiner points. Moreover, they designed a constant factor approximation algorithm for this problem. There are numerous works on bichromatic point sets, which are often referred as the red-blue input in the literature. For instance, there are work on red-blue intersection problems, separation, red-blue connections, different variants of the red-blue matchings and the interplay of between the red and blue matchings, red-blue partitioning problems, and different type of red-blue trees. There is a nice survey by Kaneko and Kano on the red-blue points. Planarity is another important aspect in computational geometry. In fact, many of the basic structures in computational geometry are planars. For instance, the minimum spanning tree, minimum weight spanning tree, Delaunay triangulation, or Voronoi diagram, these are all planar structures. So planarity is indeed a natural criteria, and many geometric problems dealt with the crossing-free configurations. For instance, Abu Afas et al. Studied the plane matching problem. Then the edge removal and the non-crossing configurations in geometric graphs has been studied by Eichholzer et al. Long non-crossing configurations problem studied by Alon, Rajagopalan, and Suri. Then matching points with different objects and things has been studied by Alopis et al. Our results: we proved that the problem of computing a bottleneck planar bichromatic spanning tree is NP-hard. Then as a corollary, we obtained that the problem does not admit a polynomial time approximation scheme, a PTAS. On a positive side, we present a polynomial time approximation algorithm for computing a planar bichromatic spanning tree of bottleneck that is of at most 8 square root 2 times the bottleneck of a bottleneck planar bichromatic spanning tree. We note that this is the first constant factor algorithm for any variant of this planar bichromatic spanning tree problem. Let's settle the complexity status first and quickly. So the theorem we want to prove is that let P be a set of n red and blue points in the plane, then computing a bottleneck planar bichromatic spanning tree of P is NP-hard. We show a reduction from the planar three-set problem. Our reduction is very similar to the one used by Borglet et al. However, in order to make this work for the bottleneck variant, we have made some changes, and we will point out to what are the changes that are required. For the sake of completeness, let's say we are given a 3CNF formula where X is the set of variables and Y is the set of clauses, and GF is the graph where the vertex set is the union of the variables and the clauses. And there is an edge between a variable and a clause if it appears as a positive or negative literal in the clause. If this graph is planar, then we call this formula a planar 3CNF formula. And in the planar 3-set problem, the objective is to determine whether a given planar 3CNF formula F is satisfiable or not. We know that this problem is NP-complete. So given F a planar 3-set formula, we construct in polynomial time a set P of red and blue points in the plane such that F is satisfiable if and only if there exists a planar bichromatic spanning tree of P of bottleneck 1. So let's consider the graph GF, and this can be embedded in polynomial time. We start with the very simple object. So let's take a pair of red and blue points which are epsilon distance apart. Epsilon is very small value. Then we can construct a chain in the following manner such that the consecutive distance, these distances are always 1. Now one can see that it doesn't cost anything to find a connection or give an edge between within the sides. So it is to decide that how we are going to connect these sides. And it is, one can observe that if I am connecting the sides in the consecutive manner, then we can achieve a cost 1. Whereas if I do not obey this rule and try to connect it to someone that is far apart, then the bottleneck will be increased. So we will not be able to obtain a solution that is of length 1. There is one more thing. Once we decide that this blue point will be matched or connected with this red point, this enforces or this propagates through this chain, because this blue point is hidden from this side, and then once this blue point is connected with this red point is hidden, and so on. So our variable has 3 parts. One is this circular chain of sides and the spatial red point. Now here it is important to note that in the minimum weight variant, until this point this gadget works, but in case of bottleneck, once you pay a certain length, then one is allowed to pay that length multiple times. And to prohibit that, we had to introduce one red-blue chain, and this chain will ensure that we cannot connect Ri to both sides of the chain. So for this particular variable xi, as we can see that if Ri is connected to this blue point instead of this one, and then this chain above Ri will be connected to this red point, and which will in together enforce some propagation throughout this chain. We call it as a false assignment if Ri is matched or connected with this blue point, and then if Ri is connected with this blue point, then we'll be calling it a truth assignment. Now every clause Cj is represented by a single red point Rj in the middle, and there are three chains, these orange shaded areas, these three chains that are actually coming from their respective variables. Now note that there are some choices that are made in the variables, and we end up with this choice. So we say that if we end up with this blue solution where the final connection is to the blue, then it's a truth assignment. And if it's a red solution, then it's a false assignment. If this happens, then we will not be able to connect this red point to anyone here, because all the blue points, the possible blue points within of length 1 are hidden. Of course, this red point can be connected to someone, but then the length or the bottleneck will be increased. So we need at least one truth value. Finally, we connect all the variables to each other by some fixed part of the tree, because this entire construction needs to be a tree and not just a forest. But this can be easily made because this type of chains can be created, and this does not increase the bottleneck, and we do not care of paying the same length again and again. Now we show the non-existence of a p-task. Note that this edge can be, this length of this edge can be close to square root 2. So more precisely, the distance of each chain of the clause and the corresponding side on the inner circle of the variable is 1, and the distance between each chain of the clause and the sides on the outer circle of the variable is at least square root 2 minus epsilon, for some epsilon being between 0 and square root 2 minus 1. This gives us this corollary that the bottleneck planar bichromatic spanning tree problem cannot be computed within a factor less than square root 2 unless p equal to np. In particular, there is no polynomial time approximation scheme unless p equal to np. Now we move to our main result, which is the constant factor approximation algorithm. So let P be a set of n red and blue points in the plane. A bichromatic spanning tree T that may have crossings, which can be computed in n log n time, due to a result by Binias et al. In Algorithmica 18. Now notice that the bottleneck that will be returned by this algorithm, let's call it a lambda, which is the length of the longest edge in the tree, in that tree, which is also the lower bound for any planar solution. So we show how to compute a planar bichromatic spanning tree of P such that its bottleneck is at most 8 square root 2 times lambda. More precisely, we prove this theorem that given a set P of n red and blue points in the plane, one can compute in polynomial time a planar bichromatic spanning tree of P of bottleneck at most 8 square root 2 times the bottleneck of an optimal bichromatic spanning tree of P. What is our plan? The roadmap is following. Our algorithm will be comprised of 2 stages. In stage 1, we partition the plane into cells such that every cell is convex and it contains points of both colors, red and blue points. Or in other words, every cell is bichromatic. Then every cell, the distance between any 2 points is bounded by 5 square root 2 times lambda. And the cells are connected That is, if we consider the graph with the cells as its vertices, and there is an edge between two cells if they are adjacent, sharing a common boundary, then this graph is connected. We can construct a planar bichromatic spanning tree of the points in every cell in the second stage, and then we connect them without crossings across the cells. Let's start with a very simple grid partition. We may assume that the length or lambda is 1, and every square, we find a square partition where every square is of side length 3 lambda by 3 lambda, and all points are in the interior of these cells. Let's give them some names of these cells. So a cell is monochromatic if it contains only one color, for instance this one, bichromatic if it contains both colors, for instance this one, and empty if it contains none. Now we have designed these cells in a way that this can be again broken into lambda by lambda square partitions or into 9 cells, and we call them C1ij to C9ij. Let's observe that C5ij, the cell in the middle, this does not contain any points. Why? Because if it is containing any points, this point must be connected to something. But if it is connected to something, then and it's a monochromatic cell, then the length is more than lambda. But we have started with the tree whose length is at most lambda. Every point that lies in these cells, they are also at most one distance far apart from the boundaries. So from here to we get a trapezoidal decomposition by joining these cells to the corners, and then we obtain 4 trapezoids. That is, one is to the left, right, top and bottom, TLIJ, TRIJ, TTIJ, and TBIJ. In this step, our objective is to transfer these trapezoids, or so to say merge these trapezoids with the neighbor trapezoids, so as to regroup or repartition the points. So in order to do that, we construct a directed graph. So let's say that this cell Cij is a monochromatic cell. The one subcell in the middle, it's empty. Then there are edges to its neighbors that are also monochromatic. For instance, these are monochromatic, but this cell is not monochromatic, and they are of opposite color. Then we need to rearrange the cells based on this directed graph. For that, we have a complex cutting and gluing procedure that we call the cell partition procedure that breaks and merges with the neighbors. Before that, let us define the in degree and the out degree of this graph. I mean, this is simply the number of edges that is inwards to this vertex or the cell, and the number of edges that are going out from this cell to some other cells. In this case, for Cij, the in degree and out degree both are 2. So the step 1 is when the in degree is 0, as you can see here, and the out degree is greater than 0, then we apply the cell partition procedure and sort of use these trapezoids to break these cells and attach it to its neighbors. There are 2 other steps where the in degree is greater than 0, and when the in degree and out degree both are equal to 0. And in both of these cases also we apply the cell partition procedure. Now, a cell after this step is either partitioned or is extended, because if it was monochromatic before, then we must have done something with this. However, if 2 partition cells are adjacent, then we can have a situation like this, which we call looms. So in this case, we have a horizontal one, and in this case, we have a vertical one. After this step, we have 3 different types of cells. The first is the original 3x3 cells, which are the bichromatic ones, and we don't care about the empty cells. Then the monochromatic cells are partitioned and extended. So we have some extended cells, and then we have the loons. However, the loons are problematic in a sense that they are not necessarily bichromatic, that they may not contain both color points, which is an important criteria or invariant for us to maintain. So we try to get rid of them. There are involved cases to get rid of them. For instance, there are some cases here, and then there are some more cases, but the point is that we try to break these loons and then further attach it to the neighbor cells so that they become convex and they become bichromatic. This is how the final subdivision looked like. We started with this square grid, and then slowly, after doing all of this cell partition procedure, we reached to a stage where we have a partition like this. Now our objective is to build the actual tree. So there are two steps that we will be using to build the tree. One, we want to build the tree first inside each of these cells, and then we want to merge these trees to find a whole connected solution. So now we are building the tree inside each cell. Consider an arbitrary point. Without loss of generality, let's consider that point is a red point. And let's say this, let's call this point S. So from this point, we connect it to every other blue point that is contained inside this cell. And then we further extend these as if they are rays, and this will give us a cone partition of this cell. And then once we have the cone partition, there are only red points that are part of these cones, and we can safely attach it to one of these blue points that is on the boundary of these cones. But we cannot just distribute one to the left and one to the right. That may create crossing, so we have to be consistent, and in this case we just connect it always to the one that is to the left. However, there can be non-convex cones, as you can see here, for instance, but then we can take the bisector and then we partition it into convex cones and then apply the same procedure. The question is that why these trees will be planar. This will be planar, like for the sake of contradiction, assume they are not. So there must be an edge that is intersecting some other edge. And that edge is a bichromatic edge as well. If this is a blue point that wants to be connected with this red point, then the question is that why in the cone partition we did not create a cone with P. Then if it's a red point, then it will not create any crossing and it will be safely connected to A. So therefore, it is not possible to create crossings. Now we are connecting the trees to build the connecting the trees that are built inside each of these cells, and then we want to stitch each of these cells to finally construct a total solution. This is done in the following manner. We construct a bichromatic spanning tree T of P by traversing the cells starting from an arbitrary or a non-empty cell in the breadth first search manner or BFS manner. So we initiate the tree T by an arbitrary tree constructed in an extended cell. We connect it to the trees from its adjacent cells, and then we proceed from these cells to its neighbors. However, these connections are actually not very simple, and there are several interesting cases because, yes, it is true that inside each of these cells, we have successfully created the trees in non-crossing manner, but we also need to ensure that when we are joining these cells or the trees that is constructed into neighbor cells, then we do not create any further crossing, and for that we have to do some heavy case analysis. Some glimpses of these cases are here, but these are not enough and there are still some more cases. Okay, so I almost reached to the final slide, which is the bottleneck complexity and the planarity theorem. So after stage 1, every cell is contained in a square of size 5 lambda times 5 lambda. Then after stage 2, Some cell is contained in a square of size 8 lambda times 8 lambda, and some are in 8 lambda times 5 lambda. Hence, in total, it will be 8 square root 2. Then every step of this algorithm is done in polynomial time. Therefore, in total, it's a polynomial time algorithm. Here we are skipping the details of the correctness proof because of the time constraint. Because in order to show that at every step we have always maintained a planar solution, we actually have to go through every cases that we have used to stitch these trees. Okay, so we proved that we showed the theorem that given a set P of n red and blue points in the plane, one can compute in polynomial time a planar bichromatic spanning tree of P, a bottleneck at most 8 square root 2 times the bottleneck of an optimal bichromatic spanning tree of P. In conclusion, what we did is we showed that the bottleneck variant of the planar bichromatic spanning tree problem is NP hard. Even this problem is APX hard. We have designed a polynomial time approximation algorithm with constant factor approximation. And then as a part of future work, I think it's an interesting question to improve the approximation factor for the minimum weight variant to be better than square root n. And then also the question is whether we can design better polynomial runtime algorithm for the restricted instances, for instance, for points in convex position or for points on a line, etc. Thank you.